Boop, boop. Hopefully that's recording. Okay. Do you make noises when I make noises? Yes, you do. So we have recording. New people, did you sign in? No. Okay. So I think we're cool to begin. First of all, things you're gonna need on the exam. You're gonna want a pencil, and you're gonna want lead or a pencil sharpener. You're gonna want stuff to draw straight lines with. So like a ruler or one of these triangle things is really nice because you're going to be using the charts, and the professor is a lot more exact about his grading than I am. So if you're not super close to what he wants, then he'll take points off. So you're definitely going to want to be sure you can draw straight lines. And then you're also going to want probably a highlighter because you will need psychometric charts on the exam, so that can help you show what it is you want to do. So I know he went over this in class, but oh yay, more people. Sign in. I know he went over this in class, but basically what's going to be on the exam is psychometrics, pumps, room air distribution, duct systems, and fans. So I have seen the exam, I didn't memorize the exam. So if you ask me like exactly what's going to be on the exam, sorry. But these are things you should know for the exam. So for psychometrics, it's really important that you know how to read this chart. And like not just like, oh, this is what relative humidity line is. Oh no, we're not going to draw today. Okay. This is what the different lines are. You also need to know what the processes are. Like if a line goes in this direction, that's evaporative cooling. Like this is from the slide, so it's a good idea to have this, or at least know basically what different processes look like on a psychometric chart. Then you're also going to want to have saturated water tables. This comes out of ASHRAE Chapter 1, and he's got that under Lecture 3. So you can just scroll down and you can find them. Because not only the psychometrics do you need to have saturated water tables, everything needs these. This is why I didn't do that, because I was going to draw pictures. So you're definitely going to need to know how to do ACFM to SCFM. Do you all know how to, are we good on that? Do you all know how to do that? Basically ACFM, that's based on density. SCFM, everything is the same density. So part of the reason why you should definitely know how to convert those is there is going to be density related questions on the exam. So you're either going to have to figure out how to make your ACFMs work as far as mass flow goes, or you're going to have to convert it to SCFM and use a volume flow, because you can do volumetric flow, where one is equal to the other with SCFM because everything's the same density. Then other important things you're going to need to know is total heat. So you need to know your basic equations of this guy. That was more exciting than I thought it was going to be. So this is how you're going to get all of your heat stuff. Do any of these look familiar to you? Seen them before? Okay. And then you're going to have to know how to manipulate these in order to get your sensible heat ratio. And then also, if the professor asks for other things, he may not ask for sensible heat ratio. He may ask you for other ratios of these sorts of things. So he may not want sensible heat ratio. He may want like ratio of latent to sensible heat or something like that. So watch the wording and make sure you're doing what he wants you to do. Oh, what else was on here? PowerPoint, tell me what else I'm supposed to do. So besides just this, another page. You need to be sure you know how to do mass flow. Do y'all remember how to do basic mass flow things? So, like, not just like mass flow as in like the, m dot times I dot equals m dot times I dot. But also you need to know, like, for ducts and things, you know how if you have a point, the mass flow in equals the mass flow out. That's also something really important you should know how to do. And then for mass flow, that's CFM over specific volume. That's confusing it all. So on to pumps. Do you all remember this lovely table here? It's a good idea to review some of your piping stuff too, because things like converting mass and hydraulic diameters and things like that are going to come up. I don't know if he's going to be doing anything to do with this table in particular, but it's really nice because it's got all your things here. And this came from Lecture 5, Slide 36. Case studies. Oh, I can touch it and make it do things. But yeah. Important equations, we got hydraulic diameter, which is so it's important that this is the cross-sectional area of your pipe, though I don't know what other area you'd have to take of your pipe. And then the wetted perimeter, so this is the inside diameter of your pipe, not the outside one. Also important, you should know how to read a pump curve. I think I included one. So on the homework assignment, you could read the pump curve pretty wrong and still get the right answer. So I'm going to go over real quick how you would read this. So if you look, can I make my mouse thing move? There we go. People online. So if you look here by the 500 right here, this is total headed heat. And this line is a nice lovely horizontal line that stretches across. That's a horizontal line. Now see this 10.5 here? This follows this curved line. So it's really important that when you're reading this 10.5, you don't just go straight across. Because there were a number of people who did this on the homework. You need to follow this curved line. And it worked out nice for you on the homework because I didn't take off points. I didn't realize people were doing that because it was so close. But like on the exam, I'm sure he's going to pick something way out in this range, and you'll have to know how to read that right. And then it's also really important that you notice here that this is gallons per minute down here, and those are the vertical lines, and that these percentages are part of these weird, funky, curvy lines going on here. And the slanty lines here, those are your HP, your horsepowers. And then as far as reading NSPH goes, you're going to follow, like, if we're going to go for 10.5 at, say, 68%, so that'd put us right there. If you go down, you go down and you meet it down here where it meets up with the NSPH, you come over here and you read this guy. right over here. Not this for you. You don't read that side of the thing. You read this one right here. So that's just things that people had trouble with for reading these tables proper. Then definitely on the exam, you're going to have to deal with total dynamic head. And so know this equation down here, know how to get each one of these parts, and also know that you may not have to solve for each of these. It may just be given to you. You may say the suction pressure head is this. So don't go trying to calculate it if it just gives you it. So you may not have all the parts for it to look all nice and pretty like this. It may be that he gives you each one of these things and expects you to add that up to total dynamic head. So know how to manipulate this and know the concepts behind it. And so I have an extra slide. I'm going to post this all, by the way, so that way you can have this guy. And then whatever I write on the writing thing, I'll put those on Blackboard. So this is just, more of how to calculate everything in total dynamic head. Another thing that people had some issues with on the homework was which things were pump horsepowers, like what equations to use and things. Here's the equations you should be using. With the horsepowers, you calculate the theoretical pump horsepowers, and then that's when you calculate like the brake and the water and all those other kinds of things, horsepowers. So you don't ever do anything with your theoretical pump horsepower after you calculate it in most circumstances. You're going to be doing things with these guys down here. More horsepower equations, should you need those for the exam. What else do I have? Oh, pump laws. Ooh. So on pump laws, hopefully all of these are super simple and you're all like, this is why you're so boring, why are you writing these here? But these are really important, definitely, to know for the exam. And you all remember how recently in class he's been talking about the fans and things? The fan laws are almost exactly the same as the pump laws. They mirror them. So if, like, on a fan problem, you're totally freaking out and you can't figure out how to do something, look in the slides for something that looks like pump laws. And that's probably the fan laws. Because they follow this exact same pattern of just RPM over RPM, and then RPM over RPM squared, and then RPM over RPM cubed. This one is your foot rate. This one's your head. And this one is your shaft. And then you can just replace this bit here with dn over d sub 0 if you have a fixed speed instead of a fixed diameter. And then y'all know how to calculate efficiency. It's just, yeah. Throw that up. Really screwed that one up. Oh, also for this, you'll want to once again be sure you know where your saturated water tables are. And then also there's an example in lecture 8 that uses a lot of this stuff, and that's a good thing to reference if you're lost. So on to ADPI procedure. This is what's going to happen basically with linear distribution. So this is what should happen almost all the time with linear distribution. Basically, here's the ADPI procedure. You follow the steps in it. I took this also too right out of the slides, so it shouldn't be all that difficult to follow. So normally he gives you airflow requirements and room size, and also gives you reflected ceiling plan, and also gives you tables for the type of diffuser to be used. So like basically up to like half of here, it's already like he's already given you all of that stuff. So you only have to do what comes down from there. So room characteristic length. Depending on if you've got a grill or a ceiling diffuser, basically it's the distance from one object to the next closest object. So this is distance to the wall perpendicular to the jet. Normally you only have one grill in the room, so you don't have multiple ones. Or distance to closest wall or intersecting air jet. So distance to the nearest thing, distance to the wall that's across from it. For characteristic room length. And then on to the next thing is, after you find out what your characteristic length, you need to know what this throw to length ratio is. And Professor gives you this lovely chart here, where it's got what your room load is, so he should have given you that, or he's given you some kind of a number you can manipulate into that. Paste that. Sorry. And then the most important column in here after this one here is this one over here. So he'll say in the problem like you have this kind of diffuser in this sort of position or something like that. So you look for the thing that's the closest. And so usually you're going to be dealing with these two right here. Sidewall grills and circular ceiling diffusers. Might be something else down here, but like these are usually what's most common. And so depending on your room load, you'll come over here and you'll read the range. And then with this range, you'll need to use these numbers in order to calculate what this is. So after you get this, you'll need to calculate what your throw feet is, and then you can see if your throw feet is inside of that range. Am I going too fast? Does everything that I've said so far make sense? If you have any questions, you can ask. That's what this is here for. So, continuing, this is from the homework. If you remember this guy. The hardest part for the homework was I think a lot of people didn't realize they could interpolate. That's another thing. For any tables he gives you of stuff like this is a class on theory, not on a class of we're actually going to use this thing. So feel free to interpolate the heck out of everything. Actually do, interpolate. Interpolate as much as you possibly can, because if you don't see the exact number you need on that table, you're probably going to want to do that. So since you can bring basically the Earth to this exam, either like put an interpolator calculator on your graphing calculator, or pick one out online for you to do things into, because that'll speed things up. But on this, for reading this, here's your CFM. Here's your positioning. So this is your noise numbers, and then you've got your throw feet for each one. And that's, this stuff down here is the more important stuff. That's usually what you're going to have to look it up. And then the things up here, like these velocity pressures and things up here, are numbers you're going to manipulate to make sure that it fits your requirements. So it's good to come this way and then go up for most of the stuff he's going to give you. Does anyone like really just not understand this chart at all? Should I go through it more? No? Okay. And then I don't know for sure on the exam if he's going to do anything with noise criteria, but if he doesn't give you a number, this was in his slides, so he's going to be assuming that you know these numbers. So just keep an eye out for this slide. It's from lecture 10, slide number, Adobe Connect's in the way, 19. So you've got this guy, and it's just a table to tell you how big your noise can be. Okay, continuing on to this guy. Yeah, do this guy. Equations. This chart a lot of people also have trouble with for reading, so keep an eye out for this. This is also just like, we should know how to read this, because this is how you do things in the field. You get a chart like this, and you have to figure out what's going on. So for this, you've got your velocity of feet per minute, so you're going to go up whatever your throw is. And then for your throw, it's got this ridiculous picture, but just ignore that. Throw is half of your word in most cases. So if you remember, this was the question where he said 40-foot square and not 40 square feet, and everyone, including me, read it wrong because people were all like, Liz, what's going on? Things I should know. So for that, with this 40 divided by 2 is 20, so you go over here. And now to note, these numbers here are not horizontal. These are lines that are also slanty. So be sure to read them by their slanty lines. And these guys over here are also not horizontal. These are also slanty. So be sure to be able to read down with the slant. And then with a chart like this also is a class on theory, so also interpolate on this. So like if you get like up here, you get close to like say 1400. If you're close, don't say it's 1400. Say it's like 1350 or 1375, because you're acknowledging that you're not quite there. That's pretty close. And then you can use that number to interpolate. Okay. So on this, really important is Bernoulli's equation. This is the P static P velocity. This is static pressure, velocity pressure. Your head loss. This is the pressure because it's but yeah, this here is super important. In the slides, you can figure out how to calculate all of these, which is why I just have it like this. But like this here, this is where everyone screwed up on the homework, is no one really used this all that well. Well, some people did, but a lot of people didn't get to use this on this. For room air distribution, this is really important because basically it's saying that pressure in one spot is going to be the same as pressure in the other spot combined. Well, without the head, but yeah. So when in doubt, if you have like a whole bunch of pressures, this is probably what you should be using. And then if you remember hydraulic diameter that I talked about before, that's also a good thing to know for your room air distribution. And then another thing about the homework that a lot of people had trouble with was, if you remember, there was that one equation that he gave you out of the book that was like C something times P something. That velocity pressure at 0.0 is equal to velocity at 0 over 4,005 squared, and that's velocity at the section, so that's your pressure at the section. And then whenever you're doing things, you always want to compare to pressure in the common section. So for a lot of these, you get like a funny looking air duct, like you've got this guy here, and then you've got this guy here, and this guy going off there. You want whatever they share in common. That should usually be the pressure that you use in most equations in order to compare things. Because if you're comparing things, like, you can't compare two things using pressure from one area and pressure from another area. You have to use a place where they have in common. So like, if you remember the homework, there was a guy like this and a guy like this. This guy here was the common section. So this guy's here's pressure should have been the one you all were using. Which is kind of confusing, but like that's kind of how it is. Like, just with SCFM and ACFM, you go to SCFM so that way all their densities are the same, so you can compare them. When you're doing equations and things, you want to use the common section pressure so that way you can compare them. Does that make a lot of sense? Okay. Oh yeah, I even had a little picture guy. Oh, and I had Bernoulli's equation in here too. I should look through my notes before I go on a tangent. So here's all the equations for things, should you need them, because I included them. Oh, also be sure you know this number. You have this written down somewhere nice and easy to get to on your notes, because this is also like the density that you use when going from ACFM to SCFM. And just like standard air density is just definitely just a good thing to have lying around so you can use it. Okay, on to fans. So with fans, important equations with them. This was like the very first thing he had on any of his slides was this equation. So this equation here, this is your volume flow rate. This Q3 and P3, or row 3, those are CFM and the density taken away from your fan, an area away from your fan. He has the specific like wording of where they are in the slides. It's like one of the first couple slides in his fans lecture. But basically, this is just for your volume flow rate. Is you can take a ratio of using your CFM and your densities. So, like, you can use this if you have volume flow and density of somewhere away from your fan. You can usually figure out what that is of your fan in order to do things. And then also important is specific speed. Which is ns. So it's more important on this test that you know fan density things more than fan speed things, but you may end up needing to know ns in order to calculate that. So remember, ns is this guy, 0.5. It's a really convoluted thing. You're a 7. Be a 7. And then this is equal to that's your fan diameter, that's your rotational speed for the fan, CFM. And this one it's got this lovely fluid density in there. So you might end up needing that in order to get places. But I would just like keep this in mind for later on in the class too, because even if it's not on the test, this guy made back. Okay, so fan laws. Fan laws you should definitely know for the exam. Super important. Probably most likely will use them, stare at them. If you notice here on your fan laws, these are, ooh, doopity-boo. But like, you have directly proportional squared cube. Super similar to pumps, guys. Basically, a fan is just an air pump. Pump does water, fan does air. They do basically the same thing, you just talk about different things. So this is why you should like be aware of your NS. Is one of the variables that goes into that is this N value. So you may have to work backwards from the NS value in order to get N. I don't know, but just like keep it in mind. Anywhere where variables are shared is a good place to just keep an eye on it, bookmark it in your bunch of notes or something like that. So for these basically just mirror your pump laws. So you've got this guy for your CFM, you've got this guy for your pressure, and you've got this guy for your brake horsepower. This is once again like brake horsepower. We don't ever use theoretical horsepower, we just use other things. So, good idea to know those as well as you can. Yep. Okay, fan density. Definitely something you should know for the exam is fan density. This guy up here, Hubnert, if you remember him from like chemistry, physics, and all of life before now, he's back! Know him. He's exciting and yeah. But basically with this guy's a good guy to know. And then you even give you the Reynolds number, but if you have like a chemistry website or something like that that's got like your Reynolds number, you know, and heat and this and that, that might be a good thing just to like bookmark for the exam. So that way you feel confident and prepared. But he's even got like pressures and things for different kinds of things. So got a little table. This one was out of the slides too, and I didn't crop in the slide number. Sorry. Where are you from? Unknown. 13. So probably from lecture 13 is where I got this one. But if not, we post this on Blackboard, so it's all in the same place. So just like with pumps, how they had theoretical horsepowers, it's back with fans. You get a new theoretical horsepower. And it's calculated almost the same way. If you remember this guy from pumps, this is just like the simplified version of that one, that equation. So it's all basically the same thing. Good stuff. And then this is just like how with pumps, how they have a theoretical horsepower. They still got the brake and the motor and all the other ones. And then I couldn't find the table. I don't know why, because probably I just didn't look all that hard enough. Remember that table where it had what all of the official horsepowers were for things for pumps? That's a good table to have. You had to use it on a homework assignment because you couldn't just put down whatever horsepower you got. You had to look it up on the table to make sure it was one of the official horsepowers. That's a good table to have, and I'm sorry I couldn't find it, so I was going to include it in here. But if you could look for it, or like if you wrote it down for a homework assignment, then that would be a good one to have. And then I already went over how to study. Okay, do you all have any questions? I went over most of the things that people emailed me about. So, any questions in general? Does this help at all? Okay. I noticed some of you got the maroon book. That is a fantastic book to have. Also, if you had any of Professor Stevens' classes and you were thinking well enough to download all of the ASHRAE handbook charts that he gave you, that's also a great thing to have if you don't have the Maroon book. But the Maroon book is basically like the good parts version of those ASHRAE tables. So if like you got a friend who took the class who's got the Maroon book, you should get a hold of that Maroon book because it's got all these like charts and tables that I've been talking about in there, and then it's like paper and you can touch it, and go through it. It works better for me. I don't know if you like clicking on the computer better, then don't listen to me. Oh, we have comments from people. Okay, Professor Pascal says, pressure is related to what the loss coefficient is based on, so that was for... where are you? Nope. Nope. Where did you go? This guy. So pressure is related to this one right here. So your loss coefficient of the fitting. So this is what you got from your table about ducts. So this is back to ducts on like the homework assignment 4. So pressure is related to that. Professor also clarified that Q3 back in this one is the volumetric flow rate at the fan inlet. So this is what it started off as, this is what it finished as.
You said it was taken away from
This is taken away from the fan at the start of the fan. So this is what the air is like when it goes in. And this is what it turns into.
Do you have one problem or something?
Do you want an example problem? Do you all have any example problems that like he did, or like a homework problem you'd like me to go through? I didn't write any because it's really hard to write example problems for this class, and I figured people more wanted like, here's things I should be studying. But if you have like, this problem here didn't make any sense, then I can go through it. Oh no, he went entirely away. Come back. Anything else?
So, are there 6 problems in total, 6 questions?
There will be 5, so there's going to be 1 over each one of these topics. So since the exam spans 2 days, you're going to get 3 on one day and 2 on the other day.
6 problems?
5 problems. You're going to have 1 over each topic. And now, problem is a loose thing, as you know in this class, because usually they come in multiple parts.
Were you really easy?
When I took this exam, I was not properly prepared for this exam, so I really struggled busting my way through it, because I didn't, have like, here's all of my homework assignments all grouped together by topic, because for a lot of this, like, Professor clarifies. Your Q is actually, if you all want to read that, Q3 is your test plane. Your Q is actually Q1, which is the volumetric flow rate of the fan. Volumetric flow rate of the fan. Oh, test plane. Yeah.
Is it what?
If he does anything to do with this, you'll be able to figure out from the questions what you need to do. That's actually another thing about the test is what he gives you, it's a good idea to write down all the things he gave you and be all like, what do I know that I can turn all of these things into what I need to get? So if you have like, say on, Bernoulli, say if you have like a whole bunch of pressures, you should use Bernoulli's equation if you're talking about like ducts and things. It's really, a lot of this class is like figuring out what you have so that way you can get to where you need to go. Because the hardest thing I think about this class is all of like the extra things, because like you're all like, well, I have all these numbers, what do I do now? And it's really important that instead of panic, you're all like, well, I'll write down what I have. Here's all the things the professor gave me, and then look at the slides from recently and be all like, here's what the other things that I can use in order to get from point A to point B. And everything on the test is going to be something you've seen before. It's either going to be modeled after something that was in an example, or something on the exams, or something that, you know, he talked about in depth as far as like problems to solve. And then he knows you also are on a time crunch too. Like, you've got a week to do your homework, so, you know, those are more intense. And with this, he knows you have an hour and 15 minutes to do a couple problems. So anything where it's like lots of calculations, super hard to figure out, probably not going to be on the exam. No, his exams are doable in the time given. I did a lot better on the final, actually. I feel like, I don't know what I actually got on the final, because like I came in a lot better prepared, and I at least finished all of the questions on the final, because, you know, I had all my notes together and things. So it's more important to like have everything organized and ready to go, I think, than it is to like solve lots of example problems. Because if you can like find an example that's kind of similar to what he did in class, or like a whole bunch of equations, that's a more important thing than to have a whole bunch of numbers memorized.
So would you suggest like a specific organization strategy then for your
Well, what I did
notes?
is I went through and I solved, per his solutions, all of the homework problems. Like, I went through and I did them when he did the solutions in class. Anything that he recorded in class is online. So if you just rewatch the recordings, like that's what I did.
He said he won't post the solution.
No, he doesn't post the solutions, but he works the solutions in class. But yeah, I solved all the things for their solutions, and then some example problems I thought would be really important, and I went and I solved those too, and then I binder clipped them together by topic. So like he said, these are the topics on the exam. I'm all like, well, I'm gonna clip those up by topic. But I work better from example problems. If that's not what you do, then I would write yourself an equation sheet or something like that, if that's something that would make you feel better prepared. And then I would print out the saturated water tables, since he's got those. It's under lecture 3 folder in the ASHRAE. You just scroll down a little bit and you'll find them. Print out those saturation tables, unless you got the Maroon book and they're in there.
Or you can help for a Snyder.
But that's a lot easier to be able to actually scribble on there, because it's hard to read them off of a computer.
Which means you got a pro.
And for people who came late, I was talking about things you should bring to the exam. Definitely bring a pencil with an eraser, an extra lead, or a pencil sharpener, and then also bring a ruler, straight edge sort of a thing. The triangle is helpful too, but yeah, just come prepared to draw straight lines exactly. And then don't take the exam in pen. If you're from another country where they make you take exams in pen, don't do that here. Take it in pencil. And then I was recommending that you print out extra psych charts in case you screw one up. He's going to give you 2, because I talked to him about it. Actually, he was going to give you 2, even though I didn't talk to him about it. But, like, it will make you feel more confident that if you screw it up, you'll have an extra. And then just, yeah, keep that there. I guess the best thing on this exam is just not to panic. It's hard, but it's doable. For those who took Stephen's classes, it's not Stephen's exams. You can finish it in the time given.
Thanks. At least something.
Yeah. Anything else?
Too many things that I don't know.
Okay.
Maybe you should start dying.
Good luck.
Okay, we'll do all the homework. 5 in the exam.
Professor Pascal says good luck, guys.
Something different.
Yeah.